Hello everyone, and welcome back to AISC's Night School, Steel Construction from the Mill to Topping Out. Today is December 10th, 2018, and this is our 8th and final session, Quality Control and Quality Assurance, presented this evening by Larry Kruth. My name is Brent Liu. I am with AISC's Continuing Education Group, and I will be moderating this evening's presentation. I want to introduce this evening's speaker, Lawrence F. Kruth, P.E. Larry Kruth has been the Vice President of Engineering and Research at AISC since 2016, where he oversees all of the Institute's technical activities, including AISC standards and technical publications, research activities, continuing education programs, university programs, and technical assistance through the Solutions Center. Previously, he was the Vice President at Douglas Steel, Fabricating in Lansing, Michigan, where he spent more than 3 decades of his career. Mr. Kruth has notable expertise in fabrication and erection, quality systems, and safety and connection design. Larry has served on multiple committees for AISC, including the Specification Committee and task committees on connection design and quality control and assurance. He's also served on AISC's Safety Committee as well as the Research Committee. Outside of AISC, he is a member of RCSC, the Research Council on Structural Connections, and the SEA of Michigan, among others. He has also served as an adjunct faculty member at Michigan State University for their capstone structural engineering class, and in 2011, he was named Engineer of the Year by the Structural Engineers Association of Michigan. Larry, thanks for being here, and I'll hand it over to you.
Thanks, Brent. I really appreciate that. And let's get started on this right away. And one thing that really struck me is this is the last session, Quality Control and Quality Assurance. And when I looked at this, I started to think, this being the last session from the mill to topping out, it really struck me as unusual that quality control and quality assurance is the last thing we're talking about. Well, then I went a little further, and I looked at the AISC specification for steel buildings, AISC 360. And I looked at all these chapters, and I looked at all these design requirements, starting, general provisions and design requirements, and design for stability, design for members, all these design requirements. And the last chapter is quality control and quality assurance. So I wondered, why is this last? I gave it some thought, and I said, whenever you're doing something and reviewing something, usually the thing you remember most is the thing you cover last. So maybe that's why we're doing this last, so you'll remember it first when you're working on a job. And also, why is it last in the specification? So you'll remember it first whenever you're thinking about anything on a job. You'll remember quality is the most important thing. Also, you also will remember that steel is a very high quality product. It's the highest quality construction material on the market, fully controlled, as you've learned, from the mill through topping out. So the plan for today is we're going to do through 2 parts. We're going to go through Demystifying Chapter N in the Building Code in Part 1. And Part 2 is we're going to go applying Chapter N to statistical improvements. When we do Part 2, I'm going to show you some ways it's been applied in a fabrication shop and for erection, and how it can be used to improve quality in those areas as well. But let's start with the first part, Demystifying Chapter N in the Building Code. Before we start, though, I want to go through what most people understand is the typical inspection process that takes place on a job site for structural steel. Well, generally you'll see an owner will hire a construction manager or a general contractor who in turn will hire a third-party inspector. A third-party inspector will do inspections in the fabricator shop and also in the field for the erector, prepare an inspection report, which then gets forwarded to the engineer of record and the construction manager for them to review and to take action. Now, if you notice, there is a dotted line that goes back to the fabricator and erector. Usually a draft of that report is given to the fabricator and erector so they can take any corrective actions that they deem necessary. I'm only showing you this so you understand typically what takes place. So without any further ado, let's get into Demystifying Chapter N. What we're going to cover in this section is why was this added to the AIC specification? What is the source of these quality requirements for fabrication and erection? And what is the difference between quality control and quality assurance? And what does perform and observe mean in Chapter N? And how does all of this relate to the International Building Code? So why was this added to the AISC specification? Well, it was added to provide guidance of items to be listed as special inspection items and to assure consistent quality of structural steel for fabrication and erection. It also required documented quality programs from all fabricators and erectors. So what was the background? Well, if we go back and look at the AISC specification, also look at IBC 2009, the section on special inspection in Chapter 17 had 20 pages with significant references to outside documents for special inspection. So what did that result in? You ended up with these. These are actually some special inspection lists that were extracted from drawings back around that time. And this is what you generally would see. You would see a table that listed on the drawings verification inspection items you can see on the left. And you can see on the right, as you're going through there, you'll see the continuous and periodic and a reference standard. You'll see AISC 360, which is the AISC specification. You'll also see on the right IBC references. Like you'll see in the one column, you'll see a number here like 1704.3.3. That's an IBC reference to the section of IBC that is being referenced in that case. Going to the next slide, you'll see applicable ASTM standards had to be used for a steel identification. Also references to AWS A5 documents. Also AWSD 1.1, which is the structural welding code, and more IBC references. This is just in this one set of drawings. This other set of drawings was pretty similar to what you just looked at. Same list, verification inspection items on the left, continuous periodic reference standards, and you're going to see all those AISC references we talked about previously, AISC 360, section M2.5, A3.3, M5.5, ASTM standards, and IBC references over an extreme right-hand column. Continuing on with inspection of welding, you'll see AWS references there for D1.1 and D1.3, also D1.4. You'll see that referenced as well, and the IBC references. Now this one gets a lot more explicit in a lot of different areas. You can see it has the same inspection tasks on the left-hand side. It has the same continuous and periodic reference standards we just looked at. AIC 360, you're going to see ASTM standards listed here, AWS, D1.1, D1.3. You're also going to see the IBC references, but in the right-hand column, it shows a responsible agent. A special inspector is listed there as well. Another one that's a little more very similar, just looked at, but even more extensively. It talks about the items on the left-hand side, the inspection of steel fabricator, material verification, it's a structural steel anchor bolts, which are now anchor rods, weld filler material, erection, welding. You'll see that all listed there. The frequency, continuous or periodic, the responsible agent, and the applicable standards. You'll see a new one. RCSC, the Research Council on Structural Connections. That's the bolt standard, the bolt specification for bolts. You'll see that listed on the right-hand side in addition to the AISC and the ASTM standards and AWS. So there's something new added at this point. Another one that's very similar, just looked at, very extensively listed, lots of items. So you start to see these are very inconsistent to the point where you had this one. The owner's testing laboratory shall provide special inspection services in accordance with the Michigan Building Code for the following items. No direction. So you had something very extensive or something very brief. So what did that mean when we had to do inspections? Well, that meant the inspector had to reference all of these documents. He had to reference, you can see the AISC manual on the left, which included the AISC specification, AWSD 1.1 in the center. Then the upper portion, you'll see the ASTM standards. Then you're going to see the specification for structural joints using high-strength bolts, RCSC, the bolt specification. All of these standards had to be looked at and coordinated all together. So why was it added to the AIC specification? To provide guidance of items to be listed as special inspection items. So now, instead of looking at all those documentations we just looked at previously, instead of all of those, all you have to do is look at the AIC specification and Chapter N. All the references you need for inspecting for quality control and quality assurance for structural steel are in one location, Chapter N. It also was added to require documentation for quality programs from all fabricators and erectors. So every fabricator and erector now will have to have a quality control manual of some sort. And these can be in many different formats, could look many differently at every company, but every fabricator and erector must have a quality control manual to say how they control quality in their shop and in the field. So the driving question is, well, what was the source of everything in Chapter N? Where did this all come from? Was this all new? Well, the key to this lies in the tables. When you start to look at the tables, you're going to see tables for inspection tasks prior to welding. You're going to see welder qualification records, continuity records, WPS available, which is a welding procedure specification, manufacturer certifications for welding consumables available, material identification. You're going to see fit up of groove welds. Continuing on to inspection tasks during welding, you're going to see all these items listed. Now you see these are all listed as quality control and quality assurance items with either an observe or perform, you're going to see there. Then inspection tasks after welding. Welds cleaned, size, length, and location of welds. Welds meet visual inspection criteria. You're going to look at all this. This is all listed clearly in Chapter N. But where did this come from? Well, the key is to look at the commentary. When you go back and look at the commentary, and you look at the commentary for table N5.4-1, you're going to see that all of those things listed were taken from AWSD 1.1. Welding procedure specifications, WPS available, is in clause 6.3 of AWSD 1.1. Manufacturer certifications for welding consumables available in 6.2. Material identification in 6.2 as well. Continuing on for clauses for inspection tasks during welding, you can see use of qualified welder, 6.4. Control and handling of welding consumables, 6.2. And you can see listed on there, no welding over crack welds, 5.17. They're all listed here. This is nothing new. These are items that were always supposed to be inspected while welding. Also, when you're looking at inspection tasks prior to bolting, you're going to see similar things. Manufacturer certifications for available fasteners, fasteners marked in accordance with ASTM requirements, correct fasteners selected for joint details. Those were all taken from the RCS specification for high-strength bolting. And you can see the sections that were referenced here. Manufacturer certification available for fastener materials in 2.1 and 9.1. Fasteners marked in accordance to ASTM requirements were in certain figures. They're in 2.1, figure C 2.1 and 9.1. Everything is listed. Everything was taken from somewhere else. Now it's in one location. It's easy for everybody to find instead of using all those other references. So let's go into this a little more detail. Let's look how this would be applied. How are these inspection tasks performed? Let's look at groove welds. If you look at groove welds, it's an observed task. You have to look at joint preparation, dimensions, alignment, root opening, root face bevel, cleanliness, condition of steel surfaces, tacking, backing type, and fit if applicable. Really, it's a simple situation. You look at your groove weld. You can look at how it's prepped. You can take measurements of that groove weld, make sure it meets the criteria of the welding symbol that's shown in the drawing. It was prepped properly before welding begins. So it's inspection task before welding. If you go back and look at that again, it's just looking at these items that are listed on the bottom when you're looking at this joint. It's that simple. Inspection tasks during welding. These are all observed. These can be observed during welding. So you have to look, making sure they're following the proper welding procedure specification, the WPS, settings on welding equipment, travel speed, all these items. Well, what you're going to see is for every weld that is being performed in the shop or the field, a welding procedure specification is required. This is what it'll look like. This is a very simple form. This form was actually downloaded from AWS's website, and it's just filled out. It's a very simple form. Once you understand how the form is structured, anybody can fill it out if they understand anything about performing any welding. It's a very simple form to use. Once it's filled out, every welder then wants to make sure they follow all the procedures spelled out in this welding procedure specification. For example, setting the welding to the proper setting. The proper amperage is set for welding, making sure that's done properly. Inspection tasks after welding. What do you look for at a weld after it's done? Keeping in mind, not every weld is non-destructively tested. Fillet welds can be inspected visually. Now, there is some non-destructive testing that can be done on fillet welds, but most commonly, most problems with fillet welds come out visually. For example, welds meet visual acceptance criteria. You see all these items listed here. You're looking at crack prohibition, weld base metal fusion, crater cross-section, weld profiles, weld size. So when you look at this, very simple to measure weld size. This is a weld fillet gauge, fillet weld gauge. You just actually place this on the weld and you can determine if you are the proper size. That's a simple way to measure the weld. Also, when you're measuring a weld, you have to measure the length. What is the proper length of weld that was called for on the drawings, on the weld symbol? You can see this very simple. You stretch a tape out and confirm it was done. Very simple way to check a weld. These are simple visual checks on a fillet weld. Bolting. There's inspection tasks prior to bolting. And you can see there's issues here. Fasteners marked in accordance with proper ASTM requirements. Correct bolting procedure selected for joint detail. So let's look at this. Now if you look at this, these are bolts that are installed, and these have the proper head marking. Now these are marked as A325TC. So what are these bolts? These are actually F3125 grade F1852 bolts. This is the proper head marking for that bolt. So this shows this is marked properly. So you see if they are proper bolting procedures being used, proper bolting guns being used to tighten these bolts. You make sure that's being done. I also want to go over pre-installation verification testing. Pre-installation verification testing is required by the RCSC specification for high-strength bolts. It is required that you test 3 bolts from every lot of bolts. Now that doesn't mean 3 bolts from every keg. Every keg of bolts is marked with a lot number. Let's go to the next slide here, and I'll show you this. If you look at this slide, and you look at this keg of bolts, you're going to see a lot number listed right here. Now that lot number may appear on multiple kegs. The reason that may appear on multiple kegs is when a manufacturer is manufacturing bolts, they might be manufacturing thousands and thousands and thousands of bolts. If you look here, the quantity in this keg is 120. So the quality control that's being used in the manufacturing is it's being used to control the lot of bolts that is being manufactured, not each keg. So when that's done, pre-installation verification testing is done. Now, when you look at this, the way it's most commonly done, when you look at that, it's done in a Skidmore-Wilhelm device such as this. You can see the bolts put in the Skidmore-Wilhelm device. It's taken up to the proper tension. In this case, since it was a TC bolt, the end is snapped off. And if you look at the tension up here, you can see, it's very difficult to see in the slide, but there's a red line right here that shows what the proper tension is supposed to be, and it's over that tension, so it meets that requirement. So what's done, once that's completed, that keg of bolts, that lot of bolts, is marked as tested. You only have to test 3. That's all RCSC requires you to do, is test 3. Now, in shops, you may see something like this, bolts they use in the shop. These are actually stored in a dust-tight container at the shop, so no dust gets in on the bolt, because lubrication is critical on the bolt, especially TC bolts. When you open that container, you're going to see the bolts are in there, and take note, the lot number is listed right there. So you will be able to tell right away that has been tested. It's tied to the lot number. These aren't just random bolts that are dropped in here. So let's look at pre-installation verification as it's listed in RCSC. 7.1, Section 7.1 is a tension calibrator. A tension calibrator shall be used where bolts are to be installed in pre-tension joints and slip critical joints. Keep in mind it's only in pre-tension joints and slip critical joints to confirm the suitability of complete fastener assembly, including lubrication for pre-tension installation, and confirm the procedure and proper use by the bolting crew of the pre-tensioning method to be used. So a tension calibrator must be used for pre-installation verification testing. But I wanted to show you that there in the commentary for Section 7.1, it states direct tension indicators, DTIs, those are the washers with the little bumps on them, may be used as tension calibrators except in the case of turn-of-the-nut installation. This method is especially useful for, but not restricted to, bolts that are too short to fit into a hydraulic tension calibrator. So, what is the advantage of this? Well, let's go back here for a second, look at this slide. It states here, a tension calibrator shall be used where bolts are to be installed. So it has to be used where the bolts are going to be installed. Well, that would mean that on every job site, you would have to have a Skidmore-Wilhelm device as a tension calibrator. But by this commentary, you may be able to use direct tension indicators instead. Well, direct tension indicators are produced exactly the same as bolts are in lots. So what would you do? If you took a lot of direct tension indicators and you took those 3 out of that lot and tested them in your Skidmore-Wilhelm device and made sure they got up to the proper tension, they can then be used for tension, as a tension calibrator on your job site. It saves you from having to have a Skidmore-Wilhelm device on every job site. Skidmore-Wilhelm devices have to be calibrated. They get knocked over. They get damaged. This prevents that from happening on a job site. So how would you use this? Well, it's actually very simple. You would take your bolt and you would put it, in this case, is through a plate. And if you note, there's a stack of washers to take up the shank of the bolt, the unthreaded part of the bolt. And the DTI is placed on top of that stack of washers. Another washer is placed on top of the DTI. The nut is placed on. This is taken up to a snug tight condition. And after it's taken up to a snug tight condition, the bolt is fully tensioned. Once the bolt is fully tensioned, you then would check it with a feeler gauge. Feeler gauge requires that you get refusal of, I think it's 15 thousandths of the thickness of that feeler gauge. You get refusal at least 3 points along that washer. If you get refusal at least 3 points, that bolt has reached the proper tension. You've just done pre-installation verification testing for one of the bolts with a DTI instead of a good Skidmore-Wilhelm device. I do want to point out, this is a method that is permitted, but it's not clearly defined unless you read the commentary. But you still can use a Skidmore-Wilhelm device if you like to. So what does it look like? It's pretty simple. If you look at this test log right here, you'll see the bolt sizes are listed here. You're going to see the gap was listed here. It met the requirement. The lot numbers are listed in this column. So you can see it's just a simple log, so you know every 3 bolts from each one of those lots were tested and they met the proper tension requirement using the DTI. So what does perform and observe mean? Well, let's go back and let's look at IBC. At IBC 2000, 2003, and 2006, Section 1702 has these definitions. Special inspection, continuous. The full-time observation of work requiring special inspection by an approved special inspector who is present in the area where the work is being performed. Special inspection periodic, the part-time or intermittent observation of work requiring special inspection by an approved special inspector who is present in the area where the work has been or is being performed and at the completion of the work. You realize it really doesn't say the inspections are to be done. Well, if you look at 2009, in 1702, the definition is continuous inspection. Special inspection by a special inspector who is present when and where the work to be inspected is being performed. Periodic, very similar. Special inspection by the special inspector who is intermittently present where the work to be inspected has been or is being performed. Again, it doesn't say perform the inspection. 2012 and 2015 moved these definitions to Section 202, and it has continuous special inspection and periodic special inspection. Definitions are very similar. Special inspection by a special inspector who is present when and where the work to be inspected is being performed, and again, intermittently present where the work to be inspected has been or is being performed. But it doesn't really go into having who is performing the inspections or tell somebody to perform the inspections. Well, if we look at observe, what does perform and observe mean? If we look at 2012 IBC and 2015 IBC, continuous says it has to be on-site, and it references codes such as AWS D1.1, but not every task on every weld. AWS D1.1 in Clause 6.5.2, Scope of Examination, says the inspector shall, at suitable intervals, observe joint preparation, assembly practice, the welding techniques, and performance of each welder, welding operator, and tack welder to ensure that the applicable requirements of this code are met. In Chapter N, we label these as observe. At suitable intervals, observe. AWS D1.1 in Clause 6.5.3, Extent of Examination, the inspector shall examine the work to ensure that it meets the requirements of this code. Size and contour of welds shall be measured with suitable gauges. Chapter N labels these as perform. These must be done. You have to measure the size and contour of those welds, so those are perform. When you look at the previous one, it was at suitable intervals. That was just observe. This one is perform. You have to perform those measurements with gauges. If you look at N5, Section N5 of AIC 360, minimum requirements for inspection of structural steel buildings, items necessary for final acceptance of a weld, is based on the AWS D1.1 phrase, shall examine the work, and size and contour of the welds shall be measured. You must do it. Shall is not an option. RCSC is similar in Section 9. When inspection is required in the contract documents, the inspector shall ensure while the work is in progress that the requirements of the specification are met. So the question comes up, we have quality control and quality assurance. What's the difference? Well, let's go back to section N1 of the AIC specification, general provisions. What I want to clear up is what you see in Chapter N are minimum requirements for quality control, quality assurance, and non-destructive testing for structural steel. So it is just quality control and quality assurance, minimum requirements. You can't have more, but these are the minimum requirements that everybody must comply with. Generally, quality control is provided by the fabricator and the erector. They will control the quality of the product in the shop and the quality of the product in the field. They are controlling the quality. Quality assurance generally is provided by others as required by the authority having jurisdiction, the applicable building code, or the engineer of record or the owner. So quality assurance assures the quality was met. Quality control controls the quality as the steel is being fabricated and erected. Those are the differences between the two. Non-destructive testing is usually performed by the firm responsible for quality assurance. There is an exception in section N6. We'll get into that exception in N6 and describe that very clearly to you what that exception is. But as a general statement, non-destructive testing is performed by the firm responsible for quality assurance. Keep in mind, I did tell you that not every weld needs non-destructive testing. Some of it can be done visually. Section N2 talks about the fabricator and erector's quality control program. So if a fabricator and erector is going to have to perform quality control, what needs to be in their quality control program? They have to have procedures and inspections. How do they perform work in accordance with the AIC specification in the construction documents? All inspections must be documented, including the non-conformances and the corrections implemented. If an inspection hasn't been documented, it hasn't been performed. There is no way to ensure that the inspection was done if nobody documented it. You have to be able to document your inspections. So somewhere in that quality control program for the fabricator and erector, the inspections they perform to control their quality must be documented. Also, there's a section on material identification. They have to have a procedure to identify material. It has to comply with the Code of Standard Practice, section 6.1, and monitored by the fabricator's quality control inspector. There has to be a person or persons identified in the fabrication shop to control quality. How are they monitoring the proper material is being used? Again, the inspections must be documented. So what are some of the things that might be listed in a fabricator's quality control procedures? Shop welding, high-strength bolting and details, shop cut and finish surfaces, shop heating for straightening, cambering, and curving, and tolerances for shop fabrication. All of these are clearly spelled out in the AIC specification, the Code of Standard Practice, and those other references we mentioned, but now it's all in one place. Chapter N has all those listed. But you have to have specific procedures specific procedures in a fabricator's quality control program. They have to explain how they're going to do this. The erector quality control program is relatively similar, very similar items, except they're done in the field. So section N5.1 deals with quality control. Basically, the tasks are listed in the tables. Remember those tables we talked about previously? Every task is listed there to make sure the work is performed in accordance with the construction documents. Now, quality control is done by looking at shop drawings and erection drawings and the applicable reference specifications, codes, and standards. So you're saying, well, wait a second. We're only looking at shop drawings and erection drawings? Well, the shop drawings and erection drawings were approved by the engineer of record, and they are being used to fabricate the structural steel or erect the structural steel. Well, why are we only using those at this point? We're using those plus the applicable reference specifications and codes and standards because if you look at any design drawings, you're not going to see every detail for every joint, every weld that has to be applied, all the specialty items that have to be, bolts that have to be used. All those are spelled out clearly on the shop drawings and erection drawings, but they aren't always spelled out on other drawings. So these are used to perform quality control in a shop and in the field. Now, quality assurance uses those same documents. It uses the same tables we just talked about, but uses those same documents, but it also uses the design drawings and specifications. That is an extra check to make sure that all the information that was in the design drawings and specifications were transferred to the shop drawings and the erection drawings. So the proper information was being used during fabrication and erection. That is assuring the quality was done properly. That's why this is quality assurance, and it uses other documents. Section 5.3 talks about coordinated inspection. In this case, the same task can be performed by the for quality control and quality assurance. Inspection may be performed by one party only, either the quality control inspector or the quality assurance inspector. But if it's a quality control inspector, that procedure must be approved by the engineer of record and the authority having jurisdiction. The building code official and the engineer of record must say that the inspections that are being performed in quality control meet the same criteria for quality assurance, and I will accept those inspection reports rather than having a third party do those inspections. So you have to have confidence from reviewing the quality control procedures that the fabricator and erector produced and their procedures they have outlined will meet the quality you are going to require on the project. But that is permitted. The coordinated inspection is permitted. So how does this relate to the International Building Code, IBC? Well, if we actually look at section N6 of the AIC specification, it talks about approved fabricators and erectors. QA, quality assurance by a third party, except NDT, may be waived. So what that's saying is NDT, all quality assurance inspections except NDT may be waived if they are performed by a third party. It doesn't mean they don't get done. They still have to be done. They just don't need to have a third party do it. You can have the quality control inspector do it. NDT of welds may be performed by an approved fabricator. NDT can't be done by an approved erector. What is an approved fabricator and erector? Well, the AIC certification program or a similar program meets the criteria for an approved fabricator and erector. But even if you are an approved fabricator and an erector, and you do your own inspection, and you have documented inspections that you are turning in or made available to the engineer of record and the owner and the construction manager or the general contractor, you still must produce a certificate of compliance. Now, what is a certificate of compliance? Well, it's a document that doesn't have to be any more complicated than this. Just lists like a project name, who the customer is, the customer job number, the architect job number, the company job number, and a statement. This is to certify that the above reference project was fabricated and erected in accordance with the approved construction documents. I certify the above is true, and all records pertaining to the above are on file. And if somebody from the company has to sign and date that. That is required by IBC and also required in Chapter N if third-party inspection is waived as is required as listed here. You can have a coordinated inspection done, and those inspections done by the quality control inspector will meet the requirements of quality assurance. But you must see this document to have a company official say, yes, that's been waived. And I am assuring you everything was done in accordance with the documents. So if you actually look at the 2018 IBC, section 1704.2.5.1, it states, special inspections during fabrication are not required where the work is done on the premises of a fabricator approved to perform work without special inspection. Approval shall be based on the review of the fabricator's written fabrication procedures and quality control manuals that provide a basis for control of materials and workmanship. So if you review the fabricator's quality control manual and you observe some of the procedures they're using, special inspections can be waived at that point, and quality control inspections will be sufficient. The 2018 International Building Code requirements for special inspection of structural steel states in section 1705.2.1 that the requirements for special inspections are to be performed in accordance with Chapter N of AIC 360. So you realize steel is the only material that doesn't have a list of items that must be inspected require special inspection in IBC. All IBC says, follow Chapter N inspections, and you meet all other requirements for special inspection. So steel is the only material. All other materials have lists of items in IBC. So what does a coordinated inspection look like? It's going to be very similar to this. Owner still hires a construction manager or a general contractor. Construction manager or general contractor will then hire a fabricator and a director who will do their own quality control and quality assurance. Now, as I told you, every inspection must be documented. So if every inspection is documented, there is an inspection report for every inspection. Those inspection reports can then be given to the engineer of record or the construction manager and general contractor, or both, or it could be available for review. So we've taken out the third party. Third party is not necessary if you are confident and have reviewed the quality procedures that the fabricator and erector are using, and they are an approved fabricator in accordance with IBC. An AISC certified fabricator and erector meet the requirements of IBC. Well, remember I told you that everything listed for fabrication erection, the source of all the quality requirements, were all items that were in AWS or the Research Council for Structural Connections high-strength bolt specification. Well, there was one new item added, and I want to show you what it was. There's this item called a Welder identification system. That is not required by AWS. But we thought it was important to add. Why was it important to add? Well, if you have a welder performing welds, and you're inspecting his welds, and you find a problem, you would like to know who did that weld, who performed that weld. You would like to know maybe that person needs more training. Or maybe if it's severe enough, maybe that person shouldn't be welding anymore. But if you have their initials or their identification, you will be able to tell who that was and understand if that person has a problem with welding. So how was it done? As Brent told you, I had been at Douglas Steel for over 30 years, but this is the way we did it there. We had a list of our welders in the shop, and our welders in the shop had a symbol. And in this case, you're going to see symbols on here, which every welder had a symbol and had a number identified over here that related to their name. It was really that simple. It wasn't more complicated than that. That's what they used. So when you look at this weld that was performed in the shop, you see this weld was performed, and you'll notice a number 2. Well, if you go back to this, you're going to see number 2 was Michael Kellogg. Michael Kellogg performed that weld. So when you're looking at that weld and inspecting that, you're saying, that weld looks pretty good. Michael Kellogg didn't have a problem with that. But if there was a problem with that, profile, length, quality of the weld, you would be able to then talk to Michael Kellogg and help him, get him to somehow help you to figure out what his problem was. Maybe retrain him. Maybe not have him weld for a while. Maybe him do something else. We did something very similar in the field. And in this case, you're going to see the ironworkers listed on the left-hand side here. There's documentation that they've been trained under certain requirements here. Welder qualification training records. There's a record of what they had, any training that was done on the job site. They used their initials here as a symbol. They used their initials rather than a number. That's how they identified things in the field. If you notice this person on the bottom, there's no welding training for this person. The person didn't do any welding. So how is this done? You can see this person is performing a weld, and once the welding is complete, he then marked his initials right there. And if you look very faintly, you can see a BR right there. So who was that? And come back to here, and you'll see a BR right there. That's Ben Roberts. So now you know that weld was performed by Ben Roberts. So when you look at that weld, you'll be able to tell that Ben Roberts did it. Did he know what he was doing? Was there a problem with that weld? You can inspect it at that point. And you can see if Ben Roberts needs any additional training. Well, I want to show you this. Now, I want to make this clear. This is not a requirement of Chapter N. This is something that we did just to make sure we had an extra level of quality control. Remember, Chapter N is minimum quality requirements? Well, this is something we did as a fabricator and an erector to make sure we had an extra level of quality control. We used a bolter identification system, very similar to the welder identification system. We had assigned either letters or numbers to each individual who was doing the bolting. And you can see this person is doing the bolting. He has put the bolt in. He's tightening the bolt to the proper tension that was required. And once it's complete, he's adding his number on there. This is in the shop to indicate that he has completed the bolting of this joint. So we know if there's any bolting problems. There's loose bolts in the joint. Because if you know when you install TC bolts, they have to be installed in a certain pattern, certain condition to make sure you get all plies in firm contact. So if you see a problem where plies are not in firm contact, you have loose bolts in the joint, you want to know who did it. The person needs to be retrained. We did something very similar in the field, and if you look at the center of this picture, you're going to see a PM. So the person who bolted this joint was PM in this case. Now, as I stated, all this bolting that I'm looking at this case was this bolting identification system is not a Chapter N requirement. It's not required anywhere, but it was something we added as quality control because we thought it might be a good idea to add an extra level of quality. It didn't take much effort to do. One of the big questions people always ask, how do I do field inspections? You know, do I crawl around? Do I have to check every bolt? Do I have to check everything? Well, if you have used the proper training for bolting and you do the pre-installation verification testing, make sure your people know how to install bolts, in this case using tension control bolts, you can inspect those pretty much visually. Welds, as I said, fillet welds, if you don't have any full pen welds, can be inspected pretty much visually for size and for length, so it doesn't take a lot. So this is sort of like a field inspection report. It doesn't need to be very complicated. If you look in the first column, you'll see an area designated by column grid lines. You'll see AM to AF and A1 to A3. Levels 2 and 3 are all pieces installed, yes. Bolts installed per procedures, yes. Field welds, all locations detailed, yes. Who did it? the date that it was done, and what items in the right-hand column were still incomplete that needed to be done. Just some things to think about when you're looking at this. It's a very simple way of approaching that. So let's look at a summation of this section. Why was this added to the AIC specification? It was added to provide minimum quality standards for steel construction and to assure consistently high quality steel construction, all in one location. What is the source of these quality requirements for fabrication and erection? It is only listing in one location the requirements of other codes, such as AWS and RCSC, the bolting specification. Only the welder identification system was added. That's the source. It was stuff that was supposed to always be done, but now it's in one location. It's easy to find. What's the difference between quality control and quality assurance? Quality control is provided by the fabricator or erector. Quality assurance is provided by a third party, normally, not always, because coordinated quality control and quality assurance inspection is permitted by the building code. What does perform and observe mean? Perform inspections must be done on each joint, each weld, each bolt. You must perform those inspections. Everything must be done. Observe, our inspections must be done on a random basis. Not each joint, not each bolt, but it has to be done on a random basis. Well, how does it relate to the International Building Code? Well, if you look at IBC 2018, it referenced AIC specification, AIC 360 Chapter N, as all the requirements for special inspection for structural steel construction. No other requirements are listed in IBC, just Chapter N. So Chapter N is recognized as the only source for special inspection by the building code. Well, now that we got through that, let's look at some ways that you may be able to apply Chapter N and how you can use statistics to improve quality. Now, I'm going to show you some things that I had done at Douglas Steel in the past. Some ways you may be able to apply Chapter N. Some things you may need to look for. So what would be in a quality management system? Well, typically you're going to see specific procedures written for engineering. We're talking about detailing. You have to see a contract review process, a document control process. How do you control all the design documents that are coming in? How do you control all the documents you're producing? There has to be a procedure you have to have. Each one of these require a procedure. How do you prepare drawings? This might sound rather simple, but every fabricator has detailing standards, fabrication standards that they try to use. So there have to be drawing preparation procedures. Now, some fabricators do detailing in-house, not very many anymore, but if you are subletting detailing to another fabricator, those procedures may be different than what you do in-house. How do you pre-qualify them? How do you make sure they know they're following the proper procedures to produce the drawings properly? How are you making sure they are doing what they're supposed to do to make sure their stuff is accurate? What is their quality control procedures? RFIs. You have to have a procedure spelled out of how do you produce RFIs? How do you track RFIs? How do you track RFI answers? How do you determine if an RFI answer is a cost change to the project? That must be spelled out. Drawing issuing. When you issue a drawing to the shop or to the field, how are you making sure that you're issuing it? How are you documenting that it is being issued? Drawing changes. Drawing changes happen all the time. When we get the design documents come in and you get new design documents come in. They cause revisions in drawings, which change detailed drawings and erection drawings. How are you making sure the most current shop drawing or erection drawing is in the right location at the right time? How are you documenting those changes, which ties back into drawing issuing, not just the initial issue, but the issue of the changes as well. And how are you reporting nonconformances? There's potentially nonconformances that can happen in the drawing process. How are you reporting those? Each one of those procedures have to be spelled out in the quality management system. That's what you should be looking for when you're reviewing a fabricator's quality management system. There also needs to be specific procedures for fabrication. What procedures is the fabricator use for purchasing material? Remember, there has to be some material controls. How are you getting that material, making sure the proper material is being purchased? You have to have a documented procedure for that. There are times fabricators can't perform all their work in-house. They might have to subcontract work to another fabricator to help them. Many times a structural steel fabricator will sublet some miscellaneous work. Sometimes they need help with specially fabricated items or if there's a very large job. What procedures are you using to pre-qualify that other subcontracted fabricator? How are you evaluating their quality control procedures? How are their quality control procedures meeting your quality control requirements? You have to have a procedure how you're doing that. How do you identify material when you receive it? Material, when it comes from a mill or from a service center, has to have some kind of an identification. How are you identifying it? Operation procedures. Well, every operation in the shop, whether it be cutting steel, welding steel, drilling holes in steel, you have to have a procedure how you're doing it. That procedure has to be spelled out within the quality management system and how you're ensuring that meets the quality of the project. Welding and bolting procedures. Sounds rather simple, but remember all those tables we looked at in Chapter N. How are you meeting those? How are you meeting all those procedures? Surface preparation and painting procedures. Surface prep has to be documented. How are you preparing your steel? What if you have a hand wire brush procedure or a powered wire brush procedure or a blast procedure? You have to have that procedure all spelled it out. And you have to make sure you have the proper procedure to paint as well. All the while this is going on, your quality control inspector has to do in-process inspections. And maybe some of the people that are welding and bolting do some of their own inspections before the quality control inspector looks at it. So in-process inspections may be documented. You may have a welder who performs a weld, does a weld, lays down a weld, a fillet weld. He wants to check with his welding gauge, is it the proper size? Is it the proper length? He may do that in process. And then the quality control inspector on his final inspections may come back and do the same procedure all over again and document that. Again, a procedure for nonconformances. What happens when a mistake is found? How are you reporting your nonconformances? You have to have a procedure spelled out to do that. Erection. Erection is going to be really similar to what we looked at. You're going to have bolting procedures. How are you bolting in the field? Welding procedures. And this is something that's rather unusual, but it may be something to think about. Site-specific safety plan and a site-specific erection plan. To control quality, you have to know where your crane is going to sit on the site. You know how to get material into the right location. Well, that's your site-specific erection plan. And how do you perform all this work safely? Well, that's a site-specific safety plan. Now, you may want to look for these. Now, I'm not going to say the site-specific safety plan and the site-specific erection plan are a requirement in Chapter N. They're not a requirement in Chapter N, But you may want to look at these. You may think that these may be good things to have and be able to see in a quality management system for an erector. Also, last, as in everyone, a non-conformance reporting procedure as well. So, how did we do it at Douglas Steel? How did we deal with non-conformances? Every non-conformance was submitted and compiled by our engineering department. Why? Well, the engineering department had prepared the shop drawings and prepared the erection drawings and had all the design documents. So they could look through that, look through the non-conformances, and they could actually see what actually took place. They would document the root cause of the non-conformance and share the situation with everyone at our weekly production meetings. I said, evaluate the root cause, and also determined if was there a quality procedure we had that was broken. Or one of the procedures we had in our quality manual, was there something that needed to be changed to make sure this didn't happen again? So I'm going to show you some examples of some things we did at that point. This is actually a rather simple one here. If you look at here, it's you can see it's a post-delivery nonconformance. You can see the piece mark 30B4. The right end has 4.5 inches down to the first hole. It should have been 3 inches down to match the girder. It was a detailing error. So how do you fix the problem? The resolution was field weld the clips to the beam at the correct location. So in this case, it was a very simple problem. It was a nonconformance. Here is the solution to the problem. This was reported and documented, as you see here, to everybody at Douglas Steel at the time. Here's another one, 57B1. Clip angles at the left end of the beam were missing. The shop forgot to put them on. So how do you fix it? You send new clip angles to the field and have them installed in the field. Again, a rather simple solution to a problem by just doing that. 862F1. Now this is a rather interesting situation. Here at the time, the erectors were trying to install a frame, and they thought it wouldn't fit. So they cut it apart. And when they cut it apart, they couldn't get it back together. So they called in and said, we made a mistake. We cut the frame apart. We shouldn't have done that. What can we do? And when that happened, we just built a new frame and sent it to the field. So that's pretty much the situation that happened with that one. Okay. This one is a little different. It's a more extensive problem. 123B1, and this was also on erection diagram E21-1. Beam was detailed with a temporary bolted connection for field welding at a later time. The field weld detail was not shown on the erection diagram, the E-sheet. It was a detailing error. Beam field welded after notice because of a bolt failure. So the solution was detailers to cut details on E-sheets during the detailing process to help keep this from happening again. So let's go through this a little bit and explain to you what took place and what the ultimate solution was. This is the detail that was actually on the erection diagram at that point. Now if you look on the left, you're going to see 123B1, and you can see this actually is an HSS 20x8 by half. And in this case, for some architectural reason, the deck was laying on this angle that was welded to the bottom of this HSS. The connection that was used was a plate that was welded to the column with a slot in the HSS and temporary through bolts being placed, 2 bolts per connection as required by OSHA for erection purposes. That's what was shown on the erection diagram. Was actually, the connection was to be welded, but it was not shown. This is the condition that occurred in the field. They poured the concrete you see in this area here, and you can see the bolt. This weld you see in this case was put on as an emergency condition after the bolt bent and failed. Has a few other pictures here. It's a picture from the other side. You can see the bolt is deformed. It has bent, failed. All it was a piece of all thread that was put through there. Picture from up above, and you can see the failure that occurred in this case. This is what the detail was supposed to look like. It was supposed to have a fillet weld top and bottom to weld the tube to the plate. That weld symbol was missed in the detailing process. That's what caused the failure to occur. So that generated not only a non-conformance, but a corrective action. We had a problem with the way we were detailing. So you see here it says detailing checking of shop drawings, non-conformance for the month of February. Drawings not prepared in accordance with the project requirements. The beam was detailed with temporary bolted connection and was intended to be field welded to complete the connection. The field weld detail was never cut on the erection drawings, therefore the beam was never fully welded. So, the temporary bolted connection failed when the load was induced. That was very obvious. This happened in 2011. So what was the root cause? The detailer did not cut the section to indicate the connection was to be field welded. The checker didn't catch that the field weld was missing. If the checker had looked more carefully, he would have found out that there was to be a field weld there. So a new detailing procedure to add a note to the beam in the model as it's being detailed that a field weld detail will be required on the erection diagram. Also, detail cut will be added by the detailer to the erection diagram, alerting both the detailer and the checker that a field weld will be required. So what does that mean? This is something that might be a little confusing. All of our jobs were modeled 100%. Since all of our jobs are modeled 100%, while the modeling is being performed, a note can be added that a field weld needs to be added at this location. The checker was using the model to check the detail drawings that are being produced. He didn't use the design drawings to see that there needed to be a field weld there. Because the checker was using the model, he matched the model and the detail match, he never picked up on the field weld. So the new procedure is the detailer, while the modeling is being done, will put a note that a field weld is required at that location, and there will be a detail cut to show that something needs to be done there. So even if the detailer misses it on the drawing, the checker will have a check to make sure it is not done again. So this was a corrective action. So what did that warrant? Well, if you actually look at the engineering standards at that point in time, these were a controlled document. They were issued to everybody who was in the engineering department, and everybody in the engineering department got a controlled copy, and each controlled copy was numbered, and they were issued and approved. This note, this line was added to everybody's controlled copy. When detailing a member that requires field welding, place a section bubble cut on the erection view where the welded joint occurs, alerting both the E-view detailer and the checker that the field weld section is required. That simple note was missing previously, and that's why the error occurred. By adding this note, we did a corrective action to make sure that would not happen again. This happens to be another situation I wanted to point out to you. This is a little different. This was a job that we were building for another fabricator. He asked us to help him build some beams. Well, when he went to build these beams, these are the details that went in the shop. And you can see there's clip angles on the end, and there's a 5.5-inch gauge. I'll just point this out. These are clip angles on the end, and a 5.5-inch gauge shown in those bolts, and those for the bolts and the clip angle. Well, again, we had these angles. He gave us the CNC files for our automated equipment. We took these the clip angles, and we took the CNC files and put them in our angle line, and this is what the angle looked like. There's no holes in that angle. The clip angle didn't have any holes in it. So what did that mean? Well, this happened to be done on the night shift. So our night shift foreman looked at this detail and said, oh, well, wait a second. I see 5.5 inch here. So if I just take that angle and I divide that 5.5 by 2 and use 2 3/4 gauge in each leg of an angle, this will work. So he made all the angles. So he made the angles and he fabricated the steel. Well, what happened is we dealt with the non-conformance. And it says here, non-conformance, holes not provided in the CNC file for the angles. Holes added manually in CNC file at incorrect location. Holes were incorrect. Why were they incorrect? Let's back up. When you look at this angle, and it's difficult to see, there's a piece mark on it here. 6A209. What we didn't know, and what the fabricator who was fabricating this didn't tell us, A209 is his standard designation for 2 9/16 gauge in that angle. If you remember, this is what the angle looked like when it went in the CNC file. It wasn't 2 9/16 holes, but our CNC operator on our night shift made his own judgment incorrectly. So what was required? Well, first of all, the CNC operator was not supposed to make that judgment. He was supposed to call somebody in the engineering department to ask them what's supposed to be done, even if it's at night. He was allowed to call me at night at home for that answer. But we required now final inspection of all the pieces to make sure that would not happen again for that entire job. We actually had some post-delivery ones. We had some of these beams that were fabricated and sent to the field before it was caught. In fact, that's how we found out the problem. The erector called and said, the holes aren't lining up. So we had to make new holes, new angles, clip angles, send new clip angles to the field for the erector to install. Take the old ones off, put new ones on. So this required a corrective action. There was a problem. There was an improper fabrication issue. A large amount of angle was provided with improper hole gauge. Original CNC file was provided with no holes, and the hole gauge was added manually at the angle line. This hole gauge was not correct. Angles will need to be replaced. So what was the root cause? The CNC files were not correct. CNC file was manually adjusted to add holes. Holes were added in correct dimension. Angles were welded on in the shop and not caught by the fitters. The fitters, their last step they should have done at this point is they should have looked at this drawing and measured this 5.5 inch dimension. If they had tried to measure that, they would have discovered that that dimension was not correct. It would have been too large. It would not have worked under those conditions. So the fitter didn't do what they were supposed to do. So angles were not checked in the final inspection process. There was a mistake made. So we needed some re-education, retraining of the people in the shop. It says, increase final inspection to 100% for this project. Create procedure. If any item is not correct in the CNC file, that item may be fixed upon approval from the engineering department. Place the item on hold until the engineering department can be consulted. That was clearly explained to everybody. Training will be provided to CNC operators to have any fixes to CNC files to be reviewed, approved by the engineering department prior to being fixed. That is the procedure that was done and the correction that was done on this project, so this would not happen again. I think the situation was the night shift CNC operator was told to get these pieces out that night, and he just hurried up and proceeded without going through the proper procedure to check. This is a breakdown of nonconformances actually for the month of August and September. I know the printing is really small here, but it shows the breakdown of nonconformances that occurred, every nonconformance and that occurred in the shop, wherever it occurred, shop, field, detailing, wherever it occurred. This is a little easier maybe to look at, and I'm actually going to blow this up a little bit as I talk about it to make it even easier to look at. I'm going to show you the top of this. This shows you some totals from statistics for 2014 and 2013. I'm going to point out some things. If you look, the percentage of nonconformances for each year. In 2013, shop nonconformances were 28% of the nonconformances reported. In 2014, 59%. That's a lot higher. Looks like something's wrong there. Detailing was at 37% in 2013, 20% in 2014. Sublet detailing was 26% in 2013, 8% in 2014. Well, we must have got rid of a bad detailer that year. That's what it looks like. Supplier, well, this is nominal, 0 to 1%. It's pretty small. Field nonconformances, 7% in 2013, 10% in 14. Well, if you look at the field and you look at the shop, you say, is our system working? Well, let's look at this a little more detail. If you start to look at this, there's a breakdown of job numbers over here, and you can see a pie chart which actually shows which jobs constituted the highest number of nonconformances. And you can see 25, 26 had 15%, the biggest slice of that pie right here, a number of nonconformances that occurred. So let's look at some statistics. This goes back to 2005 and looks at the number of nonconformances. In 2005, we had 81 nonconformances, and if you start to look, you see numbers starting to rise to a high of 141 nonconformances in 2012, and you see it drop off a little bit, 14. But you can see this number getting generally larger as you're going down. Well, why is that getting larger? Why is that happening? You must have something wrong. If you're getting more nonconformances, your quality program is not working. You're having more problems that are showing up. Well, that's one way to look at it, but that's not necessarily a good way of looking at it. This is a better way to look at it. What is the cost of those nonconformances as a percent of yearly sales? And you can see these are all around 0.2%. That's extremely low. Extremely low. Most quality programs tell you if you can keep your nonconformances as under 5% of your annual sales, you have a great, great program. When you're down to 0.2%, it's pretty hard to make it any better. But why did the numbers of nonconformances get larger? Well, what ended up happening is the people who were reporting nonconformances realized you're reporting nonconformances to improve the system. You're not reporting nonconformances to report that somebody has a problem. You're reporting that maybe something else that is in the system, something that's being done in the drawings, something that's being done somewhere in your procedures is causing those nonconformances. And maybe something can be done to correct those nonconformances so the number reduces. But again, when you're around 0.2%, even at 141 nonconformances in 2012, you're doing an excellent job. That means that people are more comfortable of reporting problems to try to make the system work better. So keep that in mind when you're looking at nonconformances. The number of nonconformances being low does not mean that you are doing a good job. It might mean people are not comfortable reporting them. I'm going to leave you with this last slide here. The bitterness of poor quality remains long after the sweetness of low price is forgotten. That quote has been attributed to many, many different people if you look it up on the internet, but it's very true. High quality will outshine everything all the time. And remember, steel from the mill to topping out is a very high quality product. I think at that, Brett, I think we'll take questions.
Okay. Thank you very much, Larry. And we do have a few questions from the audience. But before we do that, we'll do a couple polling questions as we have every week. Just a reminder, if you do have a question, feel free to submit that at this time. Okay, let's do our polling questions. Here's our first one. This is a true or false question. True or false? In an AISC certified fabrication shop, required non-destructive testing, NDT, of welds can be waived by the authority having jurisdiction. Go ahead and click on the radio button that you think is the correct answer. Again, true or false? In an AISC certified fabrication shop, required NDT of welds can be waived by the authority having jurisdiction. Okay, give you about 5 more seconds if you want to participate. All right, I'm going to close poll and look at the results. Wow, look at that, Larry.
That's very interesting.
50-50 on that one.
So do you want me to give him the right answer?
Yeah, what do you think the right answer is, Larry?
Well, the right answer is false. And you have to read the question very carefully. In an AIC certified fabrication shop, required non-destructive testing of welds can be waived by the authority having jurisdiction. If you go back and look at my slide, which I don't remember the slide number at this point, but I can tell you what it says. It says third-party non-destructive testing can be waived by the authority having jurisdiction. It doesn't say, there it is right there. It doesn't say you can waive NDT. NDT still must be performed. It just doesn't have to be performed by a third party. So keep that in mind, that NDT still must be performed. The authority having jurisdiction can waive third-party non-destructive testing if the fabricator is approved, which means like AISC certified fabricator or similar program.
Okay, good. Those interesting responses. So, okay, let's see how we do on the next question. All right. Pre-installation verification of bolts requires how many bolts per lot to be tested? The answer 3, 5, 7, or 10. How many bolts per lot must be tested when it comes to pre-installation verification? All right, I think we've got everyone's results in that wants to participate. And on this one, Larry, overwhelmingly, people said 3. Do you agree?
And that is the correct answer. 3 bolts per lot. Not 3 bolts per keg, 3 bolts per lot.
All right, very good. All right, with the time we have left, we'll respond to questions we got from the audience. Here's our first question. Do observed inspections have to be documented?
The answer to that is no. Observed inspections do not have to be documented. That's inspections have to be documented if they are performed. If they're observed, they are randomly observed, intermittently observed on the job site or in the fabrication shop to make sure everything's being done in the proper procedure. But every perform must be documented.
Okay. I'm going to go to slide 28. Sorry. Let me go to 36, actually. Nope. Apologize. Here we go. The question is clarification. We're looking at the inspection task after welding. So if looking at this, are we saying that every weld gets inspected?
Yes.
That means there's an inspector performing that inspection for each and every weld?
Yes. Those are perform tasks. That's each and every weld must be inspected. So that's why those are perform tasks. I think if you go to the next slide, I think there's a slide that references I don't know where it is, I can tell you, but it actually references what AWS says. And it talks about you must check every weld. These are the clauses from AWS. And I'm trying to see if I can find this for you real quickly, Brent. I think it's under the perform and observe section. So.
Okay, I apologize. I'm not finding it right away here.
Well, I'm looking real quickly too. Bear with me for a second. Okay, that's observe. AWS D1.1 Clause 6.5.3 says the size and contour of weld shall be measured with suitable gauges. So that's every weld. Every weld size and contour must be measured with suitable gauges. I saw the question actually asked, does two people have to do it? Well, it has to be a quality control. If you go back to that previous slide, the QC was a P and a QA was a P as well. So does it need to be two people? Depends on whether you're doing coordinated inspection or not. But it is a perform task for quality control and quality assurance. So it has to be done twice, whether it's done by one person as a coordinated inspection or whether it's done by two different people. Somebody doing a quality control inspector and a quality assurance inspector.
Okay. I'm going to go to slide 90. When you discussed the welder identification system, you talked about, quote unquote, you will know if there's a problem or if a change needs to be made with the welder based on the welder identification system. So the question is, who is that person that can make that decision? Is it the owner? Is it the inspector? Are we talking about the fabricator himself?
Well, yeah, it could be all of the above, but it really is more, I look at it more as a quality control. So it would be the fabricator. As a fabricator quality control inspector is looking at that weld, measuring those things we just talked about previously, and it sees a problem with the weld. A fillet weld that's undersized. Begins to see a fillet weld that's under length. Sees a fillet weld that is not laid in an even pattern. And if you actually look at, I'm going to jump to this slide, you can see that weld looks nice and even all the way through there. But you may see some fillet welds that aren't nice and even all the way through there. May be not the right size, may not be the right length. And you have a welder identified that did it. That can tell you there's a problem with that welder. So the quality control inspector should be able to identify it, and it helps the fabricator and erector know if they have the right person performing the work.
All right. Very good. Well, that's all the time we have for this evening. If your question did not get answered, we will work with Larry to provide answers and send those out within about a week or so.